Thank you, Wojciech. So let me just briefly introduce Wojciech. The way the audio is set up, he'll be able to hear us if we have questions. And people can mute and unmute themselves to ask you questions to Wojciech. So Wojciech from Purdue University, of course, my academic father, right? He's the director of the Science and Technology Center for Science and Information at Purdue. You all know him because he's just so closely connected with the AofA community, and he's also worked in information theory and network modeling and bioinformatics. He's got 2 books that are pretty important for our area, and a third one that he's writing on analytic information. Wojciech's a fellow of the IEEE and the AAIA, and he received a Humboldt Research Award. And then he's received Purdue's highest research award called the Arden L. Bennett Award. He was the first award winner of that award in 2015. He's been on the steering committee for many, many years. He's a friend and co-author of many of us in the community. He's made a huge impact on my life and my family's life. I'm very thankful for him. And so sorry that his lecture has been delayed for 2 years. So the keynote is the 4th Flajolet lecture. So the lecture prize was awarded to Wojciech in 2020, and he should have had his lecture in 2020, but because of COVID, it's been delayed for 2 years. So we're looking forward to hearing what you have to say, Wojciech. I'll emphasize this lecture is given in honor and memory of our friend Philippe Flajolet. And we'll have a second lecture this afternoon for the 2022 recipient, Szpankowski. So kind of a exciting day, exciting way to kick off the 33rd AofA. So any questions before we get started? Everything is okay? Everybody online okay? Wojciech, I think the floor is yours, my friend. Thank you for coming.
Okay, thank you, Mark, for the introduction. Thank you, AofA community. I wish I'm with you in person. I wanted very much. Unfortunately, my back had a different idea, so I'm trying to do it online, and let's see how it works. So you know very well that Philippe Flajolet wanted us to work on the different techniques in analytic combinatoric and expand it as much as possible, but also you know that he wanted us to apply analytic combinatorics to non-trivial problems, whether it is in algorithms, number theory, or information theory. Today, I will talk about the analytic approach to information theory. Many of you contributed to this. As you mentioned, Philippe Jacquet, Brigitte Vallet, Michael Dmota, and many others. But Philip also wanted us to move forward. So the theme of this talk is to apply analytic information theory to see whether we can move a step further and try to apply it to problems on machine learning. So the talk is, I will introduce first the problem in machine learning, online learning. Then I will review some problems in analytic information theory, and also give you a graph compression and go back to machine learning and see what we can do. So online learning, we all know how it works because Google is doing it every day with us. They look at our previous buys, and they are based on our profile. They are trying to predict what happened next so they can sell us or give us the best advertiser, so they can gain something. Once we actually click, then they have to decide whether their prediction is good or not, and depends on this, they have to adjust the algorithm. So this is actually a game where we could represent it abstractly as a game between a learner, which is Google in this case, and a nature, which is basically us. So here how it goes. So it goes in rounds. In machine learning, they call it T. So T1 to capital T. In information theory, capital T is R. And a learner receives a feature vector, which is d-dimensional vector, and makes a prediction. which will be denoted YT hat. The important thing is that the prediction is a continuous variable between 0 and 1. Then the nature, you click and you see, so either the labels, your predictions, either -1 or 1 or 0, 1. I will use mostly -1, 0. So at each round T, there is a loss. The loss, what you predicted, and the loss that actually the real level. And of course, you would like to minimize total loss. But this might not be the smartest way to do it because you always will incur some loss. So you want to compare your loss to something that is achievable, and which in machine learning is actually a set of experts. So total loss is the first sum here from T equal 1 to T. This is the algorithm that actually incurs the loss. The second part is nothing else but a comparison, and you are trying to compare to the best expert. The expert are actually a set of class of functions, and we will see some of them. Now, the whole talk is showing that the loss is logarithmic, okay? So that's what we're gonna do. The question that we have is, how actually the class of function, class of expert, impact the behavior of what is here in the box, which is called point-one regret. Let me explain this again in a picture. So, important thing is that we understand the problem. We have environment and nature, U, that generate set of labels and set of features, the dimensional feature. They descend to set of experts and to algorithm, prediction algorithm, which make a prediction. Set of experts make their prediction, and you compare these two. You compare your prediction to the best expert within the class. What we will actually focus is something that is called fixed design minimax regret. So first of all, why it is fixed? Because I will assume that the feature vector is given to me in advance. Okay, that's what it's fixed. Why it is minimax? Because I want to find the best regret for the prediction and for the worst set of levels. We can do it differently. Instead of doing this the way we do it with fixed x of t, we might do sequential prediction, and every step I'm getting an feature, then make a prediction, and the nature is trying to give you the worst sequence. This is called sequential minimax. I will not discuss it today. We will focus on fixed design minimax. Now, my claim is that this problem, a simpler version of this problem is basically universal compression. Here, by the way, first of all, I will stick to the notation and the no n, what is in the machine learning T, and there is no x. Here, the class of expert in nature is basically class of sources, set of distributions. What you would like to do, your job is to find a universal distribution Q that in some sense approximates the best, the whole class of distribution, because you don't know which distribution from this class will be actually used. Now, what does it mean best? Best means in the code length. So log of 1 over Q is the code length of the algorithm of the distribution that you selected, universal one, and you will compare it to the best one from the class. So you see there is some similarities. What we will be interested in here is minimax redundancy, which is a kind of a regret for logarithmic loss, which is I want to find the best universal distribution for the worst sequence, and to minimize the difference between the code length, the real code length, at the best you can have. Okay, so this is the problem, and you can see it's similar to the previous one. The theme of this talk is the following. We worked for 20 years on regret or redundancy or minimax regret for information theory. And I claim what we learned there can be used to the online learning. And so here's the plan. I will first discuss few results using some flageolet for universal compression regret. Then I will show you one example compression of graph. And then I will go to online regret and see what we learned can be used here. So first, the expression for the redundancy that we got is too complicated to analyze. So let's see if we can simplify. First, I define P star, which is the maximum likelihood. What it is basically normalized supremum over all distribution over the class S. And then you can see the following. So here's my minimax redundancy. I'm gonna add and subtract log of this sum. What's happened now, you can see this log supremum of this probability. When I bring the minus under this one, I'm gonna get P star. And what it stays here is plus log of the sum. Now, we will choose universal compression. How to do it algorithmically, a different story, equal to P star. We know that this, from Kraft inequality, we know that it cannot be a negative. So this is actually minimizing it. So that I can make it 0, and I get log of this sum. This sum in blue here is called Szpankowski sum. And the whole talk is about how to compute the Szpankowski sum. And we will see, depending on S or H, and how to compute supremum and summation. This is basically our job. So this is basically the connection. So let's start. So I'm talking about a universal compression. We have different class of sources. We can have memoryless sources, Markov sources, or more complicated. For memoryless sources, if P sub I is the probability of seeing simple I, then this product, when K sub I is the number of times symbol I occurs, this is empirical distribution. And for the Szpankowski sum, I have to compute the supremum over this. By the way, this is universal, means that I don't know P. I have to estimate it. And you can see that if you do supremum, you are getting product of this four, which will be throughout the talk. K sub I divided by something, in this case, A to the power K sub I. If I sum it over all K sub I, satisfying this is my Szpankowski sum. How to estimate it? I will give you the results. For Markov sources, the problem is more complicated because you have Pij, probability of transition from symbol I to J. Kij is the number of pairs Ij, but these pairs overlap. So this is a little more complicated. It is, you have to deal with Markov types, and we did it. But still, supremum has similar probability. Product of K sub J over Ki, Ki is summation over J. I will give you results for this too, but I will focus and show you some actually derivation for a different source. Renewal sources for two reasons. This is the more general source. It has infinite memory. And second, this is my first paper with Philippe Flajolet. So I want you actually to focus on that. So what are we going to do? First, we summarize what's happened in memoryless K. We using singularity generating function, tree function, and singularity analysis, we can get a full expansion of minimax regret. Actually, when I did it, I used Bruno Salvi, the computer algebra, and this was very nice. I would like to just explain to you intuitively what is the first term. So look. There is m-1 unknown parameters, p1, p2, pm-1. M is the size of the alphabet. That's m is fixed here. I have to estimate them. When I estimate it, I'm making an error. The error is basically this normally distribution, Gaussian distribution. And actually, the non-exponential term, polynomial term, 1 over square root of n is what decides about this. So for every unknown parameters m-1, I pay a price of log n over 2. This is throughout sources that have finite memory. For Markov, the work that I did with Philippe Jacquet, it is again the same. You have how many unknown parameters? You have a matrix m by n. By the last column, you can compute from the previous. So you have m minus one unknown parameters. For every one, you pay log n over 2. And the difficult part was to compute the constant. That's what we did with Philippe in 2022. Now, I'm not going to prove it. I will show you something more complicated than this. We're going to go to a renewal sources, which has infinite memory. How it works? I have a distribution Q over positive integers, and I will generate a sequence of length n. How am I going to do it? In the following way. I start with 1, then I use Q distribution and generate an integer, and this will be run of 0. In this case, this run of 0 is of length alpha 1. After that, I put 1. Then independently, I pick up another Q distribution, generate another run of zeros of alpha 2, and I do it until I get a sequence of length n. Okay, so this is my sequence. You can see that the memory is not finite here. That was the model introduced by Chisar and Schultz. They were managed to prove that the redundancy goal like square root of n is not anymore logarithmic. With Philippe, actually, we computed the constant and more. This constant, you will see it related actually to the integer partition. So this is what I would like to do. I would like to show you how we can derive this result. So I start again with the sequence. There is a problem, of course, because there is some trailing 0, which is not a complete distribution Q. This gives some technical problem, but nothing else. So this is my sequence. And let K sub m be the number of alpha that are equal to n. So the number of runs of length n, K sub m. Then the probability of a sequence is not difficult to compute because I have K0 runs of 0, K1 of runs 1, and so on, plus the trailing 0. This trailing 0 again gives some technical problems, but actually, if you do supremum over the blue part without the red part, you are getting again the same what we saw before, memoryless of Markov. Ki to k. K is basically summation of ka. The problem is that this product goes up to n. It's not the finite like before n, the size of alphabet. It's the same n as here. Now, because of the trailing 0, actually the start of sum is bounded between two parts, and but the thing that is interesting is Rn, or actually Rnk. Rn is summation of Rn over k, but Rnk is what you expect. You have the product. K is the summation of k sum r. The product is up to n, not up to fixed. It is going with n. You have, of course, Newton coefficient, but the summation is interesting. It is over an integer partition into k terms. Why? Remember, this sequence is of length n. It has k0 runs of 0, k1 runs of 1 plus 1, 1, so it's 2. K sub I runs of length I, zeros plus 1, so you multiply by I plus 1. This is exactly the partition of an integer partition. And k, we need this k as a summation of this. Again, this is n. So here's the thing that we want to do. We want asymptotics of R sub nk and actually Rn. If we do it, we should be able to understand the redundancy. The problem with the sum is this green part, the Newton coefficient. So we have to, and it doesn't, you see, this is convolution, so we are perfectly fine. But this doesn't fall into convolution. So what we're going to do, here's the plan. First, I want to tell you that for Rn, we have much better asymptotic expansion. And here's the plan for the next 3 slides. I will replace Rn by something simply Sn, that when I can use convolution. Then I use combinatorial calculus to actually express Sn as a product of 3 functions. Then I use Mellin transform to analyze it around some singularities. And once I have the singularities, we have to apply saddle points to finally get the redundancy. So this is the plan. Let's start it. So Sn is almost like Rn, except that instead of Newton coefficient here, I replace it by Stirling. So you see I have E minus K here. Now everything looks beautiful because this is actually a product, which I can express as a product of a generating function, which I show you in a second. The problem is how to grow from S to Rn. Philip, I remember it, we were driving for a dinner here at West Lafayette and come up with the idea that this relation between Rn and Sn could be done through introducing random variable, which is basically a product of Snk over Sn. You can see that this is easily expressed this way, Snk is here. Then, if you compare this to things, you can see that everything reduces to Stirling approximation, Kn factorial and Stirling approximation, which we can express this way. So if we know some probabilistic concentration of Kn, we are basically at home. And indeed, what I will show you is I will focus on finding Sn, but we can also have compute the expected value of K and the variance. Then Chernoff or Chebyshev will help us to actually see that this can be actually computed as expected value of the square root of 2 pi expected value of Kn. That's what we need. So the goal is for the next 2 slides to show you how to compute Sn. Okay. So we introduced tree generating function. The real tree generating function is here. You know it. It's k to the power k minus y k factorial vk. Here I have k to the power k and e minus z just to simplify it. You can say that beta z and tn is related this way. The same in memory sources. And we know very well tz, how it behaves. It's lumbar function. So we know all singularities that we need to deal with. Now, how it is related to our original problem? Remember, we want to compute Sn, Snk, and Sn. So let's introduce the first generating function, summation over k, and then summation over n. Once I have SDU, Sn is basically the nth coefficient of SDU1. So what is SDU? And here the beauty of another combinatorial is coming in. Remember, it's that z to the power n, but n has this integer partition. Then you have the u to the power k, but I can split it like that. Ek also goes into this one. And the product. You can see very well that this is the convolution of this kind of terms, except that you have z to the power I, because instead of ki, you have this coefficient I. So this is infinite product of a modified tree function. And we have to analyze it around z equal 1 or z equal 1, and just to get expression for z1, a singularity expansion, for which we should be able to compute Sn. Let's go. So here what we do, instead of SZ1, we compute log of this. Why? Because at z equal e minus t, this has a nice expression that falls under harmonic sum of the Mellin transform. When we compute it, the Mellin transform of this function L is basically a product of zeta function plus lambda s, which has an expression as a product, as an integral, but fine, we can deal with this. And you can see, of course, that the singularities of L star Mellin are at 1 and at 0. Now we have to deal with this. And what happened? We use converse Mellin transform. I'm putting under rank a lot of technical issues. And you can see that we can expand it around z equal 1 as much as we want. And the constant C, the lambda one is basically what we call constant C, and you can compute it actually in this case that is pi square over 6 minus 1. Pi square over 6 is also related to integer partition enumeration, so it's not a surprise. But that's not end of the story, because remember that S of this is exponent of this, so we have such an expression. At around z equal 1, this expression blows up, so you have to apply a different technique. I simplify saddle point method because there is a lot of technical issue of estimating the error term, but in principle, the leading term can be estimated relatively simple. So for any function f of z that grows like exponent a 1 minus z, log 1 minus z, and so on, you basically simple application in the main domain of the saddle point give you this expression, which is translated to what I show you for Rn. So that's how we did it. So you can see a lot of library here. I would say they are beautiful, and I enjoy working with Philip on this problem. Okay, so this is the part that basically show how analytic combinatorials can be used to compute the redundancy. But you might ask a question, why to bother? Why to compute redundancy? Okay, so here's the philosophy of universal compression information theory. The information theory is about finding lower bounds. So for compression, we know it's entropy, and then you are trying to find algorithms like Lemper-Diff that actually for large N achieve this entropy. The problem is large N. There are millions and billions of algorithms that converge to entropy, but how quickly they converge is the issue. It's very important because for practical purposes, you want to compress to the optimal value for a relatively moderate value of N. So what we're going to do, this redundancy is helping us to get the lower bound. Redundancy tells you what is the best you can achieve in the rate of conversion. This is the first part of the problem. The second, and then I show you in few slides how to apply it. You basically would like to have an algorithm that achieves this, let's say, the leading term of the redundancy. In this case, we need only upper bound for the code length of the algorithm you design, but you want that it achieve this lower bound redundancy, because then you have at least some assurances that within the class of the distribution, memoryless, renewal, markup, your algorithm is asymptotically optimal. So this is when redundancy played a role. I will do something else. Information theory was mostly about sequences, but we have to go to more complicated data structures, graphs. This is one thing, and structural relationship. This is what the center of science information was. How much information are there in structure? What do I mean by this? Okay, so this is an example of, I will explain everything in actually very simple case. So let's say I want to draw all possible level graphs on 3 vertices. You can see there are 8 of them. But if you look at unlabeled version, which I call a structure, there are only 4 structures, 3 isolated nodes, 1 edge, 2 edges, 3 edges. I want to know how many bits do I need optimally to compress such a structure when the graph generated is by some model. It might be very complicated model like preferential attachment, but I'm gonna do something simple for you. I do Erdos-Renier, which has nice analytic combinatorial there too. So we know that the best you can compress this level graphs to the entropy of this level. this structure to entropy of the structural I call it structural entropy. So the first thing you would like to find the relation between these two. Now, where is the redundancy? Actually, in this case, we will try to compute entropy of the structure up to 3-4 terms and want to actually match our algorithm to the 3-4 terms. And the second term is where redundancy comes in. Okay. So where is the problem? Okay, let's go back here. You see that the probability of this structure is actually probability of one level graph here times the number of distinct level graph that give you the same structure. So where is the problem? Let's look at this simple graph. Here is a graph on 5 vertices. If I perturb these vertices, I can do it on 5 factorial ways. I have the same structure. Really? Now, there is some symmetry in this graph. So if I switch B and C and D and E, I'm getting exactly the same adjacency matrix. So the number of distinct structure is not 5 factorial, but it's 5 factorial divided by 2. What is 2? 2 is the cardinality of the automorphism, which is agency preserving permutation. So we need to understand better for a graph the cardinality of the automorphic group. There is another issue, by the way. Here I say that every permutation 5 factorial is legitimate, but some graphs construction might not allow it. But let's assume that in our case, because we're going to do Erdos-Chenier, every permutation is allowable. So what is the relation between these two? First of all, notice that every permutation of distinct levels give you the same probability. So basically, the number of a distinct structure in this kind of case is n factorial divided by the automorphism. If I take log of this, then I'm getting the entropy, and the relation between level graph entropy and structural entropy is here for the simplest possible model. But still, we need somehow to know how to estimate the automorphic group, at least the log of that. So this is our job. I will talk now about the compression of special graph, Erdos-Chenier graph. Remind you that Erdos-Chenier graph on n vertices works like this. I'm taking a pair of 2 vertices, and with probability P, I put an edge. I will assume that P is fixed here just to simplify. Sudakov and others prove that if P is not too small or too large, the graph is asymmetric, which means the automorph is basically one with high probability. Then I know what to do, because I can remember graph entropy was the level graph entropy, which in Erdos-Chenier is very simple. What it is? Imagine you have an adjacency matrix n by n, and you randomly put 0 and 1 in every vertex. It's independently. So every item in this matrix is entropy HP, and the n choose 2. So this is entropy of this level graph. But minus log n factorial coming from here, the automorph is not much, but this n factorial plays a role. We also can do asymptotic partition property, saying that if I randomly choose structure, is basically bounded by this one. But that's not the job that I want to do. I want now to design an algorithm that matches the first 2 terms of the structural entropy. And n log n, it's easy to match the first one. So let me give you an idea again on an example. Let's say I have a graph. I put labels so I can explain what I'm doing, but I want to compress the structure, no labels, and I compress it into two strings, C1 and C2. And I will be growing here a tree because that actually explains what's going on. So what I'm going to do, I'm going to pick randomly one node, I, and what I will store in C1 is the number of neighbors, not what is the label, but the number, in this case, 4, 1, 2, 3, 4. So I'm storing the number of neighbors, nothing else. Then I split the whole graph into neighbors of I, D, F, G, J, and non-neighbors. The next thing, I'm gonna delete I and the edges. This is the graph that I have after executing the first part. Then from the neighbors, F was here, you can see here, F was here. I'm gonna choose randomly one of them. I'm gonna choose F, and then I store number of neighbors of non-neighbors in both left and right part of this tree. And I continue this. At some point, my graph looks like this, and there'll be isolated nodes. These isolated nodes are important because they will determine actually the compression, and I will store information about them, which means 0, 1, in C2. So you see, I also denoted that isolated node in the associated tree as square. So here what happened, here was how it will look like. And then, by the way, I also do arithmetic encoding on C, which I call B1, B2, just for your information. So this is the original graph. The compression is concatenation of these two strings. And the associated tree is here. The second, actually, B2, length of B2 is the determining the asymptotic, which is related more or less to the path length of this associated tree with the square nodes. Now, what is my job? I want to show that the code length of this algorithm matches the first two terms of the structural entropy. And that's what I'm going to prove to you in 1 or 2 slides. And actually, it worked quite well in practice. Okay, so my job is right now to show to you, I think it's 2 or 3 slides, that the maximum code length, summation B1 and B2 tilde is because of additional compression, matches the 2 first terms. And here we use a little Flajolet, and you know my favorite tree structure try. So what is B1, B2? You remember, whenever I did go to, I always executed this associated tree to the left. Once I did everything with the left tree, I go to the right tree. And what did I store? The number of neighbors, which is basically log of the number of vertices that go through this vertex, through this node in this tree. Except when I did move to the blue part, the square, n of x was 1. So basically, the B2 is the number of square nodes, a path length through the square nodes in this associated tree. Now, to analyze it, we actually introduces a D trie that works like this. I have n balls in the root, and with probability P, I split it to the left and to the right. You can see here, but there is parameter D. From the depth D and above, I will delete one node. This node, these red balls, you remember that the algorithm, I have to take one of the node, it was node F actually, that I have to take it out and try to find the number of neighbors, no neighbor. Now, we really need only D equals 0, but to analyze it, we actually need generative. So this is the path length in this D trie because of n factor here. Of course, we have to split left, right. So we have K guys going to the left. But at D is here replaced by D minus 1. But this is a big problem because I told you we first executed the left tree, which is K node, before we go to the right one. So this looks like the D on the right side is not D minus 1, but plus K, which is a random value. We have to analyze a recurrence like this for general D. Now, when D goes to infinity at regular tries, and we analyze to death, and it was Knut and Philip Flajolet that actually show us how to do it. We know there is some fluctuation if P over Q is rational or not, but we know everything what we need to know. But that's not what we want. We want to find the difference or finite D between the recurrence that I show you and the try. And that is actually interesting because this grows like log square of n. And I will show you one slide only how to prove theorem 7. So here what I want to analyze. The following recurrence, D minus 1. Of course, we use Poisson transform of this. Then we iterate it and we get ADZ is AD minus 1 PZ as expected. And after iterating, I have ADZ, A0, PDZ. However, A0 is what I need to analyze. When D is equal to 0, I told you that is the key. And it's not difficult to see from the recurrence that I show you, it basically satisfies functional and differential equation. G here is generating function of try that we know how to do it. So we basically need to analyze this for large D because we use Poisson transform. To no one's surprise, because of this PZ and the derivative, we use Mellin transform, which has a little more complicated expression. We have S minus 1 and S. We have to iterate it again. We will get complicated expression, but the residual assurance there is a triple pole as S equals 0 and some other poles, and complicated depoissonization basically gives you log square n. So this is how we can analyze it. And to summarize it, this analysis shows us that this simple algorithm compresses the structure of a graph, Erdős-Rényi graph, up to the first two terms. This n log n is important. So that's when the redundancy comes in. Okay, I think it's time to go back to machine learning. I remind you again what the problem is. I have environment and nature, which generate this time not only string of labels, but also features, d-dimensional vector. Algorithm makes a prediction, but also we have set of experts that make prediction, and I want to compare my total cumulative loss to the loss that the best experts can do. Now, formally, it is like this. Again, fixed design, that's what we're going to analyze over class H. We know in advance the feature vector. We want to find the best predictor for the worst sequence of this point-point redundancy. And here info over class H. Logarithmic loss. And here what I will do, I will reduce the problem to class H, which we denote CPW, that basically this H, this is prediction what expert did, is basically probability, some probability with some constraints that we'll discuss in a second, that is only a function of scalar product of the feature vector, feature vector and a weight vector. A weight vector is basically, we give every expert some weight, and the whole idea is to choose the optimal weight. Let me do first a warm-up example. Let's assume, which is very often happen in machine learning, we assume that this probability is basically a logistic function. Notice that it only depends on the scalar product of these two. So what is the Starkov sum? First of all, the Starkov sum is over W, because that determines the distribution of the product. K is basically is the number of times y equal -1, level 1 is there. If you do supremum, you can see that optimal is basically log over kt minus k. If I put it here, what do I get? I get our familiar function from memory-less sources. It was for n equal 2, binary alphabet. In general, this P of W might be general and W satisfies this property, but what is important? In this case, we basically borrow what we already did for Szpankowski sum for memory less, and we find that in this case, the regret is 1/2 log T plus something else. Is that simple? Unfortunately not. Or maybe fortunately. Let's consider a very simple extension. Let's assume that now, okay, let me go back because this is important. I do it for D equal 1, dimension 1, feature vector, and more important, all features are the same. Active 1 or non-active 0. I don't consider non-active. That is important. So what is the expansion that we're going to do? We're going to assume that feature has few values, consider even 2 values. But in that case, we consider the feature vector has n different vectors. And of course, now T, which is the time that we run our algorithm, is split into T sub I, where T sub I is the number of times that I'm using feature, or T sub J, not feature AJ. A very simple extension. What's happening in this case? Yeah, now our probability, and remember, we want to find supreme of a W, is more complicated. It's the product of AJ here and 1 minus this one, which is, by the way, minus here. We'll change this minus is to plus. The Szpankowski sum again is supreme over expression. If you work on it, you'll get expression like that. Finding the supremum is not that trivial because it is multidimensional. It lays on a hyperplane that depends on AJ. And if you do analysis, we did it with Philippe Jacquet and Gil Shamir, for the simplest possible function, a logistic expression, you are getting much more complicated function. You have d-half log T that you will see always in this kind of expression, but this constant, okay, it depends on X and D. It is much more complicated. It's basically square root integral, square root determinant of a matrix. The matrix is coming from here because it's AJ transpose. So you can see a simple extension gives you much more complicated expression. We did it for fixed D. That is not what really we wanted because D usually grows with T, and then finding expression for this might be difficult. Okay, let's go to the original problem that I wanted to solve. Right now, I don't have finite number of features. Feature belongs to it's a d-dimensional vector for every T. My expert function basically is the probability that depend on this color. Actually, if you see this probability is nothing else, this function, but can be interpreted as a probability that the level is -1 condition on X, T, and W. W is a weight vector that is associated with every expert, and WX is a scalar product. So this is now I want to compute minimax regret, fixed minimax regret, when I consider much larger class of function. And again, there are not finite number of features, but more. So again, our familiar Szpankowski sum that we learned from information theory is here, but supreme of W. The probability in this case is a product of two things. When the level is -1, you multiply by B. If it is 1, you multiply by -B. And we will introduce one more notation. L of T is basically minus log of this probability. Remember, so what do we have to do? We have to find supreme of W of basically this expression and see what's happened. There is one more thing that I need to tell you. This analysis only works under a special assumption. The first one, I would like to point out that the first and second derivatives of log of P and log 1 minus P might be bounded. And also these two quantities might be convex. You will see if I drop any of this, things change drastically. So here's the result. I will show you through the slides how to prove it. You have d half log t as before. There is a constant or an expression which is quite complicated. We still have trying to understand that expression. It is square root integral the square root of this function. It turns out, and we learned it only recently, that this b is actually related to Fisher information. This b depends on p derivative and p, the function that I told you, under the assumption that the first and second derivative abide. Now, we are doing it for large d, growing of t to 1/3. So this function grows with t, and it depends on x. So if I choose x, special x, let's say we choose unit that x belongs to the unit sphere, and we consider p being only logistic function, we were able to compute with Philip the constant, and then the regret depends on d half log td. This first term, d half log td, is what you expect to have it for large t. Okay. So I have two or three more slides to finish it, basically giving you the idea of the proof. First of all, and I have about 5 minutes, so I have to be careful. So we express the Starkov sum and a complicated double integral over RD. The reason for this is quite simple, because W star is basically a solution of the gradient of L. And we know that it's unique because we're assuming log P and log minus P convex. If I denote by G the gradient, then what we can do with this function H, which is basically what appears in the Starkov sum, we can compute the Fourier transform. Here, going from here to here, we just use H equal by T. This is the determinant of this function, which will be important. That's what is the B coming in. And when you compute the inverse Marin transform, you basically get this expression. Okay, so we need to somehow estimate it. But there is a problem. It turns out that the logistic function is very important. It has very important property that Hessian. And you remember, you expect that there will be some subtle or Laplace method when Hessian will play a role, like it was in information theory, is independent of y is equal to this matrix B, which is a Fisher information. Once we know it, basically, we can use multi-dimensional Laplace method for D growing not farther than T1/3. That allows us to find this expression. Here, by the way, we use very important property as for multi-dimensional Laplace. We did tailored expansion of our expression, and we required that the first two derivatives are bounded. That's why we got this expression. Otherwise, it might not work. So the last technical slides, what happens if P of T is not a logistic expression, let's say probit function with normal distribution. Now, they depend on y, but expected value is the same Fisher information. And if we assume that the random variable, what we need to do, we basically want to show that this Hessian is very concentrated around the mean, and we did it. And the rest is basically going the path that we expect to go. We basically apply multidimensional Laplace methods, and the exponential growth cancel out, and what stays is the sub-exponential growth represented by that. Okay, I finish with one more slide. First, by the way, there is still several open problems. First of all, this multi-dimensional integrals, there are some convergence issues that we need to solve for different classes of functions. But here's one extension that I would like to see. What happens if W and X lies, lie on a manifold? That is important for quantum extension. So think about quantum extension of machine learning when the data is quantum data. And there is a second thing that I summarized in a table. What happens if assumption H doesn't hold? Let's say the second derivative is not bounded. If we consider general Lipschitz function that does not have this assumption about the second derivative, it turns out that I don't have d half in terms of log. We can find function, Lipschitz function, that grows like d log t d and lower and upper bound. So there is a question which class actually gives us d half. We know that bounded second derivative, but that we know that we can. That is not if and only if. There are some others, classes of function, that the growth of regret might be actually polynomial, not log, t to some power. So, but this result in this table were obtained by non-analytic technique, and it would be actually nice to see whether we can apply our techniques to actually understand for much bigger class of H. Okay, thank you very much to all my co-authors and AF community for giving me this opportunity. Thank you. Any
questions for Wojciech?
I see there are some chats. Let me see.
I didn't look in the chat, folks.
No, there is not much question. So there is, okay. Whether the Hessian could be zero, that's a good question. The determinant could be zero, that is a good question. For some class of function, it could be. There is still, we know very little about this integral. Convergence issue, we know only when xt going on the sphere, but we would like to understand it much better. There are some results in information theory that we learned recently that actually it's a universal compression side information. They obtain similar information expression with Fisher information. However, this was mostly for the average regret, not for the maximum. So there's still a lot of problems there to understand.
Other questions? Yeah.
I have a small technical question. I don't know if I'm missing anything, but there was a slide where you were comparing the graph entropy with the structural entropy. I don't understand why there is a negative.
I didn't hear it all.
There's a slide where you're comparing the graph entropy with the structural entropy. Can you go back to that one, please?
Sure. Let me go back. Okay, why does it want to go back? Okay, going back. This one or this one?
Yeah, this one. Like.
Yeah, it's this one, Wojciech. She's looking.
Yeah. So before you ask the question, let me tell you that this is actually the simplest possible case. What do I mean by this? We need two properties. First of all, that every permutation is feasible by the algorithm. If I, for example, apply preferential attachment that constructs the graph, it's not true. This log n factorial becomes something else. Second, very important property, that when I permute this, I'm getting distinct level graphs of the same structure. They must be equally likely for this to be true. And there are graphs like duplication model and small world. For this, it is not true. basically, this comes from the function that the joint entropy of G of S I can express as entropy of S plus conditional entropy G under S. And you can extend it to much larger class. And we did it, for example, for preferential attachment and duplication. But please go ahead, ask the question, and Mark translate it to me because I don't hear.
Is it okay? You have
Thank you.
okay, she said it's okay.
Okay.
Other questions? Questions from our friends online too, of course. You guys can unmute and ask Wojciech. I could selfishly ask a question, Wojciech.
Go ahead.
Just while you were prepping for your talk, you mentioned that you have a third book on the way. Could you just give us a hint of what you're going to discuss in your forthcoming book?
So there is analytic information theory, which is extension of a 150-page paper with Michael Dmota. We did it in the paper. We basically did known sources. When actually, and the second part of the book is for unknown sources, a lot of redundancy and so on. It is on my web. Everybody can look at it. I will send to a chat maybe later. So it is basically, it's two parts. The first part is you have known sources, and this is how to well approximate basically ceiling function and try to get the interesting thing there is, again, rationality of your rationality of P, you have a convergent mode to redundancy or non-convergence, depends on log of P1 minus P rational or not. There is a lot of work there. Then we did a compression of trees and graphs in the first part. In the second part, we basically try to understand redundancy for memoryless sources, Markov sources, and others. So that's what it is.
Okay, thanks, Wojciech. Any last questions for our speaker? Wojciech, thanks for getting the conference started on such an exciting note. We really appreciate it.
Thank you very much. Again, I appreciate it. Thank you.